From inverse square to inverse linear, onward to constant is mostly going to have to wait for another video because this is getting kind of long already. So on this page I belabor the obvious a bit because of a slight subtlety that's going to come up later. I'm talking about the inverse square law for the intensity of radiation emitted from a point source. Radiation being anything that radiates, comes from some specific source and spreads out and isn't created or destroyed. There's the same total amount of it no matter how far away it goes. So the simplest case is that an instantaneous pulse of radiation is emitted at a particular time, spreads out uniformly in all directions. At a later time, it's spread out over the surface of a sphere of some radius. Now, intensity of radiation is the amount reaching each unit of area in each unit of time. I'm looking at a single pulse, but the reasoning doesn't make any difference in the case of a sphere. You just add up the pulses over time and you've got the intensity. The steady state intensity avoids any transient differences, which you don't have in the case of a sphere. So anyway, a fixed total amount is emitted at rate r1 units away. It's spread out over an area of 4 pi r1 squared. A little while later, it's gotten farther away. It's same amount spread over an area of the sphere, 4 pi r2 squared. The intensity is the amount per time per area, so there you've got your inverse square law. Then on to the case where the source is not a point source. The next simplest source is a line going indefinitely in both directions. For the farthest that any of the radiation has gotten after a length of time is to a cylinder, and then it takes a while for the radiation that went diagonally to reach that cylinder. So you can think of it as a pulse of radiation and add up the total amount that ever goes through the cylinder, which has to be all of it. The amount per unit area is the amount divided by the area, and the area per unit length is 2 pi r L, and the amount of radiation, of course, has to be proportional to the length as well. So that gives you your inverse linear law for a linear source. Not going to get to details of the constant case, but when it's emitted from all over a plane extending infinitely in all directions, it goes through a plane a ways away, also extending infinitely in all directions. If the plane's farther away, it still goes through the plane. All of the radiation, so the intensity is independent of distance. There's your constant case in the elementary case of an infinite extension, infinite area source. On to the finite case where it gets interesting. So you've got a linear source this time of finite length L, and you're looking at the radiation arriving at a point some distance away. So you apply the inverse square law to each point of the source, and then of course you add them up with an integral. Integrate over the source and the 1 over the square of the distance. When you fill it in to make it a definite integral. You're integrating as x goes from negative L over 2 to L over 2. I stuck the point in the middle. The result is qualitatively the same, but slightly more complicated if you have the point somewhere else. So you've got dx over x squared plus d squared, and when you've got an integral, you tend to look it up in a table of integrals. If you're good at this, you've got the table of integrals in your mind, but it's still basically a table of integrals unless you have to apply some tricks. And in this case, you don't. In the table of integrals in the CRC handbook, it's number 16. They have the constant and the variable written in the other order, but other than that, it's nothing much you need to do. It's just the same formula, and it's inverse tangent. So then you evaluate the antiderivative at the end points, and you get 1 over d arctangent of L over 2d minus arctangent of minus L over 2d. And given the shape of tangent, tangent of arctangent, arctangent, tangent are both odd, of course, but the arctangent of A is the negative arctangent of negative A. Also, a couple other things to notice about the tangent, arctangent. The limit as A goes to 0, where it goes through the origin, it goes through on the 45-degree line. So limit of arctangent of A over A is 1, and then it's asymptotic as the argument approaches infinity. Limit as A goes to infinity of arctangent of A is pi over 2. So you plug in with the definite integral, and the fact that it's an odd function means that you can just have the 2 come out because they're the same, and it's adding because the odd switches the sign. And then when you take the limit as L goes to infinity, then L over 2d also goes to infinity. So the limit of the arctangent is just pi over 2, and the 2 cancels, and the d is still there, and right there is your inverse linear law as the limiting case for a long source. Now, for the limit as the source gets short, if you take the limit, you just wind up with a big fat 0, so you have to brighten the light source proportionally. You multiply by 1 over L to keep the total amount of light constant as the length of the source goes to 0. So you have the limit as L goes to 0 of 1 over L times the same expression as before, 2 over d arctangent L over 2d. And then to get ready for the next step, you multiply by 1 there as 2d over 2d. And then the 2 from the denominator here cancels with this 2. The d goes with, this d goes with that L to make the denominator here be the same as the argument there, so that we've got this part being the form that goes to 1, and then what's left is d squared. There is your inverse square law.